So good afternoon. So in this lecture we'll be looking at some of the exercises that I've suggested you do in Cameron. And this is from chapter 2, exercise 2.7. And what it is a simple illustration of the notion of choosing or selecting objects from a set and the variety of ways in which you can do it. So this is a very typical problem, the urn problem, where you have an urn and you have some balls in the urn and they have different colors. So in this case I have drawn my urn here roughly and I've indicated the 4 colors. And the question is very simply about pulling 3 of those 4 balls. Now what you can do is you can do this in a variety of ways. You can either order the balls, the 3 balls from the 4, by pulling them, for example, one by one and lining them up in a sequence so that there's a first pulled ball, a second pulled ball and a third pulled ball. There's also the notion of replacing a ball after you've pulled it before you pull the next ball. You can do it, you can pull the balls with replacement, placing them back, or you can keep them as you pull them, and those gives you a different number of outcomes. So let us consider these in turn. Of course, there's order or not ordered, replacement or without replacement. And so there are 4 possible ways in principle by which you could pull these 3 balls from the 4. And it is obvious that in order to do the counting accurately in this case, you have to understand what order and replacement means and what their absence means. So let us do this in turn. The first one I want to do is order and replacement. So this one is relatively straightforward. You pull out the ball, you record its color, and you put it back, right? So pull a ball, you pull one, let's say you pull this one, you record what it is, let's say it's a blue ball, and then you put it back and you restore the end to its original state. And then you pull the second ball because you do it of order. And you place back the second ball, and then you pull a third ball, you record it and you place it back. So it's with replacement. So the first time you put your hand in to pull out the ball, there are 4 choices, right? One of the 4 balls. Then you replace it, and so you still have 4 balls in the end. So ball 2 comes out in 4 possible ways. You could pull the same ball you had before, right? If you pull a blue ball first, you could pull a blue ball again. So that's one of these 4 choices, and then your third ball. So this is a number of ways of getting 3 balls from an urn of 4 ordered and with replacement. So this is 4 to the 3. Right? The second one I want to look at is ordered but without replacement. So in this case, you pull out the first ball, one of 4 choices, and you keep it. You put it perhaps, start from left to right as the first ball you've pulled, because you're going to order them. Then you pull out the second ball, but now there's only 3 colors left, right? You've pulled out the blue ball first, assuming. So there are 3 balls of other colors left, and you pull one of them, and there are 3 choices. And then you pull a third ball, and you have only 2 choices for that one, because after you've pulled balls 1 and 2, there's only 2 balls left. So the number of ways of getting these balls is this number of ways. In fact, 4 factorial. This is ordered, right? Without replacement. And we did in class, when we did this kind of thing, we said this is the following factorial, right? Order 3 from 4. Right? Or you read this 4 order 3, right? A set of 4 balls, you order 3 from them. That's the following factorial or the Pockhammer function. The third one is unordered without replacement. So this is more complicated. The notion of pulling unordered collection of balls from this urn sort of gives you the idea that you put both hands in, you fiddle around, you grab 3 balls without looking, and you pull them all out at the same time, right? Because there's no ordering. There's no first ball, second ball, or third ball. And this without replacement, well, how do you do the replacement, or the without replacement, when you pull them out unordered, right? If you pull them all out at the same time, what does it even mean to talk about without replacement? And so you have to think in a slightly roundabout way about this problem. So you see that whichever way you remove 3 balls from the urn, you can remove 3 of these, there's always 1 ball staying behind, right? And the 1 ball that stays behind, if you look at that 1 ball staying behind and you find out its color, then you know what you've pulled in the 3 other balls, right? If you have a blue, green, and a blue, green, yellow, and white balls, and you pull out 3 and the white one stays behind, then you know that you've pulled blue, green, and yellow. But there's only 4 choices for the ball that stays behind, and so there's only really 4 different outcomes you can obtain if you don't replace. So 4 possible balls stay behind. So I'm just going to say 1 of 4 colors stay behind. And so the number of ways that this can happen, unordered, without replacement, is 4 choices, 4 ways that you can do that. And as I've said, this is not at all that obvious, right? Because you know, we are dealing here with a very practical situation. You're pulling balls from an urn, but if I say do it unordered without replacement, it is not so clear what action you should be taking. So you have to look at what remains after you've taken the unknown action to obtain 3 of these 4 balls unordered and without replacement. And so the 4th thing is unordered again. But now with replacement. So in this case, you have to argue a bit more carefully again, because you're replacing a ball each time, but you don't want them unordered. You want them unordered, you don't want a first, a second, or a third ball. So one way you're going to do it is you're just going to count them. So you're going to classify them in all the possible different ways you can pull these balls, and then you're going to add them all up. So let us see. So the first thing you can do is you can pull a ball of the same color 3 times, right? So you're pulling 3 balls, but you don't have an order, right? So again, you can't pull out the first, the second, and the third. But the number of outcomes you can have pulling a ball of the same color is 4, right? You get one of the 4 colors 3 times. So 4 ways of pulling the same ball. Why can you pull the same ball? Well, you can pull the same ball because you're replacing, right? Now the other thing that can happen is you could pull 3 balls, and they all have different colors. And as we've argued above here in 3, in that case the ball that remains tell you what you've pulled, right? So there are 4 ways again 3 colors. Now you have to consider the case where 2 of the balls have the same color and the third ball has a different color, right? So, for example, you pull 2 blues and a green, right? Now, the first color, you have a pair and a single. Now, the total number of different ways the pair can appear, it's one of 4 colors. So there are 4 ways for the pair, right? For 2 balls of the same color, because you have 4 colors, and then you have to pull a ball of a different color, and there's only 3 colors left. So 4 times 3 ways for 2 balls of one color. Of course, this is with replacement, so that can happen. And 1 ball of another color. And so now you have to add these up, right? So you have 4 plus 4 plus 12, so there are 20 ways. And so the message you should take from here is that if you pull balls with order, the situation is rather straightforward. But if you don't have order, then either with or without replacement you have to argue a bit more carefully. Perhaps number 3 here, ordered with without replacement, is simpler, but even in this case you have to look at what's left behind in order to determine how many ways you've had. And then this one, of course, you have to argue far more carefully. So we'll come across this situation on and off as the course continues. But I think you should work through this problem very carefully and make sure you really understand the situation well. So this is the first one I want to do, so I'm going to go on to the next one after I've just cleaned the board. So the next problem I want to do is in chapter 3 from Cameron. So PJ. Chapter 3, and this is number 6. So the question says you can assume without proof, and of course this is Lukács' theorem. So we assume that 1 plus t to the power p is 1 plus t to the p, so it's equivalent to mod p. And p, of course, is a prime number. So they tell you if you have a natural number n, so you take a natural number, any natural number, 7, 10, 15, something like that, show that n to the power p, so a prime number, is equivalent to n mod p so you should show this, and you should show this by induction. Obviously, if you look at this left-hand side here, you think the binomial theorem should play a role, and of course it does. So how would you solve this? The first thing you notice, you're going to do induction on n. So you're going to assume that it's true for n, and then you want to prove it for n plus 1. And the n plus 1, if you replace n plus 1 here, you'll see up there what happens, right? So it's true for 1. It is true for n equal to 1, because if I put n equal to 1 in here, then 1 to the power p is obviously equivalent to 1 mod p. Right? P is a prime number, it's 2 or 3 or 7 or 29 or some other fixed prime number throughout the problem. So the next step, this is your base step in the induction. The next step is you assume that n to the p for this specific value of n, an arbitrary value of n, but fixed. It's at least true for n equal to 1 already, but you assume now it's true for this value of n as well. Now you do the inductive step. The inductive step, of course, you replace n by n plus 1, and you hope you can show that it remains true. So n plus 1 to the p. So what we have up here is that this is one. Well, so let me write this out. Using the binomial theorem. Yeah. Right? This is obviously true because it's 1 plus n, so there is the n. Now what you notice about this binomial coefficient is if k is between 1 and n and p minus 1, it is a multiple of p. So p, choose k, is a multiple of p if k is at least 1 and for k up to p minus 1. It is only when k is equal to 0, when it's not a multiple of p, and when k is equal to p itself, because in those cases this binomial coefficient is just equal to 1. But if I look at this binomial expansion and I look at this mod p, then of course all the coefficients are equal to 0 mod p, because they are multiples of p, except for the first one and the last one. So this is equivalent to 1 plus n to the p mod p. First term in here and the last term in there, right? K equal to 0, k equal to p. And all the others, this coefficient is a multiple of p, and so it is 0 in this equivalence. But now I've told you this, right? And so this is therefore equal to so by the induction hypothesis we have this, right? N to the p is n mod p, and so this is 1 plus n mod p. And so you have it, right? So here is the inductive step. And so that completes this problem, so not very hard, right? It's just knowing the facts about this binomial coefficient, and you can easily solve this. And of course, you use the inductive hypothesis in here, and you know it's true for equal to 1. Okay, so the other one I want to do, let me just clean the board again. Is 3.8, also in chapter 3, and it says the number of cyclic permutation on a set of n elements. So you have an n set, okay, n set, the set of n elements, how many cyclic permutations? So this is the rather straightforward one. What you have to do is essentially to write down a cyclic permutation on this n set, and then see how many different ones there are, right? So, you know, so what you can do is you can have your n set, you know, and then I'm going to write them, the elements in a sequence, an ordered sequence, and that would be a cyclic permutation. So here, I'm just writing down elements. Actually, an n is not a good choice here. Let us use C. Up to the nth one. Here's the cyclic permutation of the elements in this n set, right? So the permutation takes C1 to C2 and C2 to C3 and so on in a cycle, and then Cn back to C1. Now, this is an order, right? It's an ordering of the elements in the set, and so we know how many different orderings there are. It's the following factorial, and so this one is n, order n, because you order all n of them to make up the cyclic permutation, and so this is n factorial. Right. Next comes the next thing you have to take care of is that you've overcounted them, because some of these you write down are equivalent. They're the same cyclic permutation. So for example, if I have that one, this one is the same as that one, right? All I've done is I've taken Cn and I've put it in front, but it's still the same cyclic permutation. And so all you have to do to correct your overcounting here, you have to look at the number of starting points in this lineup, this order. And there are n starting points. You could have started with C1, or with C2, or with C3, up to Cn. And each time you get a different representation, but of the same cycle. And so what you have to do is you have to divide this by n, and so the answer is n minus 1 factorial. Right? So that's the number of cyclic permutations. Okay, so this is rather straightforward. It's not, in my opinion, a difficult problem. Okay. So let me look at the next one. Which is also Cameron, but this is also now in chapter 3, and it is 3.16. So PJ Cameron 3.16. Incidentally, the ones I don't do explicitly in this, I'll give you the solutions as time goes on, so I'll post them on the e-class page. So you have an n set, and the question is, the first question they ask is how many relations? So how many relations? Well, so what is a relation? It is a subset of the Cartesian product of x with itself. Subset of x, Cartesian product of x. So it's a subset of all the other pairs that you can make of the Cartesian product of x with itself. So let us call this x squared. And of course, what we know about x squared is that its cardinality is n squared, right? Because it's an n set. So if you look at the power set of this x squared, so all the possible subsets, then you've counted all the possible relations. So the power set of x squared, if you compute its cardinality, is 2 to the power n squared. And so this is the answer, right? This is the total number of relations you may have on an n set x. B is how many reflexive? How many reflexive relations? Instead of all the relations, all the reflexive ones. So when is the relation reflexive? That is when all the pairs XX are included. So all are element of the relation. So I've just indicated the relation here by an R. All these elements, the diagonal elements, if you wish, in this space x squared, all the diagonal elements must be in the relation. So how do you count them? Well, the first thing you do is you put all the diagonal elements inside the relation, and then you add or don't add some of the others. So if you think of this as a matrix, so the diagonal is all in. There's only one way of doing that. But then the off diagonal elements, so elements of the form xy, can be added or kept out of R, right? So all these elements here, this is when x is not equal to y, may also be in. And the word there is may. You have them or you don't have them. How many such pairs are there? Well, there are n choices for x and n minus 1 for y. So n, so this is n times n minus 1 in total. And you add them in or you don't add them in. So 2 to the power n times n minus 1 reflexive relations. I say again, so to explain again, all the diagonal elements, you put them in, and there's only one way of doing that. They have to be all there. Those which are not diagonal, but which are of this form, you have a choice. You can say this is part of the relation or it's not. So you have a choice for each of these. There are this number of pairs you have to look at, and to add or not to add, and this is a number of ways of doing it. The third one is symmetric relations. So how many symmetric relations on an n set? So just to remind you, if this is part of the relation, then you must have that part of the relation. So if xy is in the relation, then yx must be in the relation. That's if and only if. You have to add them both. So you essentially have to look at pairs like this, and they have to be unordered, right? So how many unordered pairs are there? One way you can get them is, you notice there's this number of these pairs, but they are equivalent in twos. And so you have to divide by 2 to get the unordered association between x and y. So there are 1/2 n unordered pairs. Of this nature. Let me just say here, or yx. Because if they are unordered, then this is equivalent to that, right? It's just, you've paired them up. So, now this is the case where x is not equal to y, right? Now the next thing you have to notice is that you also have the n pairs xx when x is equal to y, and so there are n such pairs. So there are n okay. So I have these two situations, this number of unordered pairs xy and n pairs which are the reflexive part xx. So in total here, if you add this up, you have 1/2 n plus 1 such pairs, right? Unordered pairs plus the xx. So these pairs are all either in, or some of them are in, or out, right? So you look at each of these, it's either in the relation or not, and then all of these n pairs are either in the relation or not, and so the answer is you have 2 to the power 1/2 n plus 1. So those are the number of symmetric relations. If you demand that a relation is both symmetric and reflexive, the argument is then exactly the same, except that all these pairs xx must now be in the relation, and so you have only one choice here for these n pairs. You put them all in, and so you have this number of choices left for a relation to be both symmetric and reflexive, and then this becomes 1/2 n minus 1. I won't do that. There's also a last one, reflexive and antisymmetric, but the argument is very simple and rather similar to B and C. So let me again clean up the board, and then we will look at another one. So the last one I want to look at is also P.J. Cameron. This is 320, so chapter 3, exercise 20. Actually, there are two more I want to do. I want to do this one, and then there is one more I want to do about recurrences. So recall that we have defined Bell numbers. And a Bell number, of course, is the number of partitions of a set, right? So if you recall that. And the question says, Bell numbers are less than factorials if n is bigger than 2. Okay? So show that this is true. So how would you do that? So what you do is if you look at the left hand side here, you have Bell numbers, so partitions of sets. On the right hand side you have a permutation. And so what sort of structure can you see in a partition of a set and the permutation? Well, the case of permutations is we can do a cycle decomposition. So you cut the permutation up into cycles, and if you look at those cycles all together, they are partition of the elements in this partition, right? So the cycles are the partition itself of this permutation, and that gives you a partitioning of an n set, right? And so for every cycle decomposition I get here, I get a partition of the set, and but this is not unique, right? Because the representation of a cycle is not unique. Is if I look at the partition of B and say, is this a permutation? Well, there's more than one permutation that you can get, and so there are strictly more permutations, and so this is what we'll argue. So if you have a permutation, of n, so if you have a permutation of n as a cycle structure, and we can write it like this. So let's call the permutation pi, and then there are n elements, and so you can, you can cut it up into right, as a cycle structure which looks like this. And so if you think of these, these things are of course a partition of the numbers, or the n elements in this n set, right? So it induces a partition of an n set. So it induces. So this structure induces a partition of an n set, and you should think of this each as a subset in the partition, right? So this is the one subset, second subset, third subset, and the union is of course the n set, right? This permutation works on the elements of this n set. It does it through the cycles, and each cycle is a part in the partitioning of that n set. So now you notice if a partition of an n set is given, So if I give you a partition of an n set, you know, so for example, and so on. So here's the partitioning, right? A partition of a set is a set of disjoint subsets whose union is the entire set. So here's the partitioning. So this this can be used to define a unique permutation. Then a unique permutation can be constructed. And so the way you do it is you look at this first part and the second part and the third part, and you turn them into the cycles of the permutation. Right, and here is now the cycles in the permutation. So I've taken the parts in the partitioning of the set, made them into cycles of permutations, and the way I do it is make it unique is I just order these elements so that they're in increasing order. So X right, I make sure that I've ordered them in that order. I can always do that. Here they're unordered, but when I turn them into cycles I order them. And so you get the unique permutation. And so what does this show you? Because the partition gives you a unique permutation, it shows strictly less than n factorial. Right? It must show that. This is the number of permutations, this is the number of partitionings. Every partition gets mapped to a unique permutation in this you know, by this ordering and turning the parts into cycles, but you can't find all permutations that way. Now, we're not done, because this is less than or equal to, but the answer, the question here is strictly less than. So, and we have now to assume that n is 2 or bigger, or we're going to have to assume that in order to make this strict. Okay, so what we notice is the partitioning into a single part. So this is when you take your n set and you just have one part of it. So this is the one part, right? So this is a partitioning of an n set. It's the partition with only one part. So this gives rise to the permutation pi with a single cycle, right? One part, a single cycle, but every time you reorder, so this is not order, but every time you reorder these, you get a different single cycle. But one might choose n factorial different, or n, sorry, not n factorial, but n different starting points. Right, so we've shown earlier that the number of cycles like this is n minus 1 factorial, and so because it's n minus 1 factorial, you only see one of those, right? N minus 1 factorial orderings of the cycle. So when is this bigger than 1? So if you see, if this is equal to 1, of course, then you still haven't proven that. But you notice that for n bigger than 1, n minus 1 factorial is bigger than 1, right? If this is bigger than 1, so if it's, oh sorry, bigger than 2, if n is 2, is 3 or bigger, then this is bigger than 1. And so this single part gives you only 1 out of n minus 1 factorial possible permutations, in which case because in this construction, when you go from the single part to the single cycle, there are some cycles you don't count, right, in this permutation. So the cyclic permutation here, you count only one of them, but there's more than one. And so this construction where you turn parts into cycles, they do not count all the possible cycles, and therefore all the possible permutations, and therefore it must be a strict inequality. And so that finishes this question. And so I have one more to do, and that is in Cameron again, chapter 4 in this case, and it is just, you know, the solution of a recurrence. So let me look at it. So this is Cameron 4.10, and it says you have this recurrence. So Fn is 2 times Fn, or 2 times Fn plus 1. This is when n is odd, and this is when n is even. And then it tells you start at 1 with f equal to 1. And so you can read this recurrence as follows. This is n plus 1. You can read this recurrence as follows. If n is odd, then you multiply by 2, so you double. Double when n is odd. If n is even, then double and then add 1, right? Double plus 1. So you would assume that there is some parity effect in here, and you have to take care of that somehow. So how would you do that? The first thing you do is, you know that f1 is equal to 1, so this is odd, right? N is odd, n is 1, and so you double up. So when you double up, you get f2, and so this must be equal to 2. Now first of all, there are two cases, n odd and n even. So let's look at the case when n is odd. So in this case, it's 2 Fn, right? And what is Fn plus 2? So you see, if Fn plus 1 n is odd, you multiply by 2. If n is odd, then n plus 1 is even, right? In this case, this of course is fn plus 1, and so this is n plus 1, and n plus 1 is even, so this is the formula that is operational here. So this is 2, because n plus 1 is even, right? N is odd, so n plus 1 is even. This is even, so you multiply by 2 and you add 1. You can combine these two. So you combine, and what you get, fn plus 2 is 2fn so 2fn plus 1 let me write it like this, is fn plus 1 is fn plus 1, so 2 of these plus a 1, right? And one of these is just 2fn. There. Right, so you get a recurrence which looks like this. This is a second order recurrence because the highest index here is n plus 2 and the lowest index is n, and then it's inhomogeneous because that's a plus 1. Now you can do the same now. You have n even and then n plus 1 is odd. And you repeat this argument and it gives you exactly the same recurrence, right? You get the same again. So, okay, so for all n, either odd or even, you get this. That is the result. You consider these two cases separately. In both cases you get this relation, and so this is what you end up with. Okay, so I'm going to rub this out. And I'm going to just move this up here. And so this is what we have to solve. So if you solve this recurrence, then you know the answer. You solve that recurrence as well. So let us now try to deal with it. So this is a slightly more complicated problem than you've seen before, mostly because of this plus 1, which makes it inhomogeneous. So what you can do is you can try to solve it in a variety of ways, but the first problem you have is you have to deal with this plus 1, because that needs you to adjust f in some way to compensate for this plus 1 each time. And so the way that you deal with this kind of question is you're going to say assume that fn is some other function gn plus a constant, and then you're going to try to determine c in such a way that the plus 1 disappears, right? And then you have a homogeneous equation which you can then solve using a characteristic equation. So let us substitute this in here. Then you have gn plus 2 plus c on the left hand side is equal to gn plus 1 plus c plus 2 times gn plus c plus 1. Okay? And so what we're going to do is we're going to cancel out these c's are just constants, so we're going to delete them on both sides here, and then we're going to try to choose a value for them so that the plus 1 disappears. So first of all, you notice that those two goes, so you have gn plus 2, gn plus 1, plus 2gn, plus 2c, plus 1. Right? And now you can see what you should do with c. If you pick c equal to minus a half, then this is 0 and you only have the g's left. So pick c. And then this term disappears. In which case you have only this left over. Right? Only these three. So this gives gn plus 2 minus gn plus 1 minus 2gn equal to 0. Okay? So now we know what to do. You're going to say that gn is equal to, some constant, let's call it d, alpha to the n. Alpha is some unknown number. As I've explained before in class, when you have linear homogeneous equations like this, they love exponential solutions. And so here's an exponential solution that we're going to try out. So you sub it in here, of course the d cancels, it is not 0. So it just cancels out. And then powers of alpha to the n will cancel out and you're left over with the characteristic polynomial. So this will be alpha squared minus alpha minus 2 is equal to 0. And this is the characteristic polynomial. Next thing you do is you have to find the roots of this polynomial. So I'll just tell you what they are. So alpha turns out to be 2, or alpha turns out to be minus 1. There. Right, one of those two values. Once you notice that there are the two possible values for alpha and they are different, they are distinct, right? 2 is not the same as minus 1, you can write down the general solution. So Fn, well, so let us say Gn is therefore equal to d times, so this is this thing here, 2 to the power n, so let's call this d1, d2 minus 1 to the power n. Right, so that is the linear combination of the two possible solutions. Of course, what I can do is, I can notice here that gn plus c is f, and c I've noticed is minus a half. So if I minus a half from here, then this becomes an f. And this is potentially the entire solution of this original recurrence. So all you have to do now is to determine these coefficients d1 and d2. How do you do it? You look at your initial choices or your initial values for f, and if you look at n equal to 1 and n equal to 2, you get two linear equations in d1 and d2 and you solve them. And so the answer turns out to be a third, 2 to the n plus 1, plus a 6, to the power n minus a half. Right? And so this is the solution here. And unsurprisingly, you see this minus 1 to the n term here. This is a parity term. What it does is it takes care of this n odd even effect that we've introduced here by giving two different rules for n and for n either odd or even. Right? So this takes care of that this is the dominant term. It gives you the growth in f n as n goes to infinity, and this minus a half compensates for this plus 1, the inhomogeneous part of the recurrence. So this is what I wanted to do in this lecture. As you see, the problems that I've given here are not very hard, but you should still work through them very carefully and make sure you get the procedures right by which you have to argue in order to solve them. Even the harder problems follow the same sort of outline, right? It's just that the arguments inside those problems may be a bit harder. But this is about the level of things that you should be able to do if you want to get through the course and do well in the exam. Thank you.